Okay, so welcome to section 4.3, which is counting. Okay, so basic counting rule. Basic counting rule is as follows. So suppose a first category, suppose a first category has, let's say, n options to choose from, and a second category, category has m, then the number of ways to choose one item from each. So then the number of ways to choose one item from each category. Is, well, let's think about this. I have n choices for the first times m choices for the second. So note, we can expand this to any number of categories. So we can expand this, to any number of categories. So what do I mean? Well, for example, let's see. So suppose you have 2 pairs of shoes. So suppose you have 2 pairs of shoes. 3 shirts and 5 pants. So how many different outfits can you put together? So how many different outfits can you put together? Okay, so I have 3 options here. First, I have 2 pairs of shoes. So I claim that, I'll call it category 1, or category shoes, how about that? The number of options is 2, right? And now let's look at the category of shirts. So category of shirts. How many shirts do I have? I just have 3. Okay. Now let's look at the category of, shall I do this in yellow? Pants. So I have category pants is 5 pants. Category, not category. Category pants is equal to 5. So I claim that the total number of outfits, so total number of outfits will be equal to 2 times 3 times 5. Okay, so 2 times 3 is 6, and 6 times 5 is 30. So I claim that there's 30 different outfits from just 2 pairs of shoes, 3 shirts, and 5 pants. That's a whole month of different outfits. That's pretty good. Okay, so another example. So suppose you can choose one from each of the following classes. So suppose you can choose one. Suppose you can choose one each. How about I call it one each from each of the following class offerings. From each of the following class offerings. So let's say we have 5 English classes. Let's do 4 Spanish classes. Let's do 7, pardon me, 7 math classes. And 6 chemistry classes. Okay, so how many different schedules could you have? So how many different class schedules? Different class schedules could you have? Okay, so let's look at the categories here. So let's see. My first category is category English, right? So English, how many options do I have for the English classes? And it looks like I have 5 options. So next will be the category of 4 Spanish classes, right? So category Spanish. Category Spanish is going to be 4 options. Okay. Now let's do the next category. Let's do 7 math. So category math. And that was equal to 7 options. And now category chemistry. So category chemistry. We had 6 options. Okay, so I claim that the total number of schedules will be 5 times 4, which is 20, times 7. Well, 2 times 7 is 14, so 20 times 7 is 140, times 6. Okay, well that math might be a bit too much, so let's do it part by part. So 5 times 4 is 20, and 6 times 7 is 42. 2 times 42 would be 84, so I tack on a 0, and there we are. So that's a number of distinct schedules we could have. Okay, so definition. So, pardon me, n factorial. That's what we're defining. So let me underline it. N factorial, denoted by an n with an exclamation point, is the product, which means multiplication, right? So is the product of all positive integers, meaning whole numbers, positive integers, up to and including n. So that is, i.e., id est. N factorial is going to be 1 times 2 times 3 times 4 times ... times n. It's a product of all numbers up to and including n. Okay, so let's note something about the factorial, because it wouldn't be math if we didn't make you suffer a little bit. We define 0 factorial to be 1, even though mathematically you might say that doesn't make sense, and it doesn't. But we define it this way in math. It's just something we have to accept. So let's consider, and let's see, I might go down to the next page for, oh, I guess I don't have to, I could break it up. Okay, so let's consider the following. One factorial is going to be 1 times, that's it, right? 2 factorial will be 1 times 2, which is 2. 3 factorial will be 1 times 2 times 3, which is 2 times 3 is 6. 4 factorial will be 1 times 2 times 3 times 4 times, 4. What am I doing? Okay, so 2 times 3 is 6, times 4 is 24. 5 factorial will be 1 times 2 times 3 times 4 times 5. Okay, so 1 times 2 times 3 is 6, times 4 is 24, times 5 is 120, right? And I can use my calculator to make sure. Okay, whoops. Well, I'm going to write this a bit differently. Do you agree that I could write this as the underline of the first 4? Do you agree that's 4 factorial times 5? Similarly, do you agree that I could write 4 factorial as 3 factorial times 4? Similarly, do you agree that I could write 3 factorial as 2 factorial times 3? Moving up, well, 2 factorial I claim is 1 factorial, or 1, times 2. And is it true, based on our definition, that 1 factorial is 0 factorial, or 1 times 1? Yes, it is. Okay, so that is, let's note, maybe in a different color green, so let's note that n factorial can be thought of as quantity n minus 1 factorial times n, as we saw in the above. Okay, so for example, so how many different ways can the letters, okay, so let me start writing. So how many different ways, And the letters. Let's do capital A, capital B, C, D, E, and F, just these letters, be associated with 6 students. So be associated. That is assigned to 6 students. Okay, so let's look at this. So the number of choices. Number of choices. Okay. Let's look at the first student. Do you agree the first student will have 1, A, B, C, D, E, F, or 6 choices? So there's 6 choices first. So that means that this is the first student. First student. And actually, let me move that over a bit. So the first student has 6 choices. But then the second student, once the first student has chosen one of A, B, C, D, E, or F, the second student only has 5 choices. So this is the second student. Similarly, the third student will have only 4 choices remaining. So this is the third student. Now the fourth student, there's only 3 letters remaining. So the fourth student. And let's go to the fifth student. We'll have only 2 letters remaining. So the fifth student. And finally, what color shall I use? Blue. The sixth student only has 1 choice remaining. So sixth student. Okay, well that looks like 6 factorial, which is a large number, so I'll just leave it annotated like that. So 6 students can choose or be assigned 6 letters 6 factorial times, which if we look up here would be 6 times 120. So that's what, 720 if we care? Okay, so let's do another example. So example. So how many ways can you assign the letters? So how many ways can you assign the letters? Once again, capital A, B, C, D, E, and F to only 4 students. Well, I could go ahead and just copy the first 4 students here, right? Let's copy all of this till I get to the 4th student. So copy and just paste this, right? because we only have 4 students in this case, right? Okay, so this is, I claim this is 6 times 5 times 4 times 3, and I can multiply anything by 1 and it remains unchanged. Agreed? So what I'm going to do is I'm going to multiply that by a very specific one, namely 2 factorial divided by 2 factorial. So I'm going to write this as 6 times 5 times 4 times 3. What is 2 factorial? It's 2 times 1 divided by 2 times 1, which is equivalent to 1. Okay? But now, what do I have in the numerator? Let's look at this. In the numerator, what I now have is 6 factorial. So I can rewrite this as 6 factorial divided by 2 factorial. But what's interesting about the number 2, 2 can be sneakily written as 6 minus 4. Okay, remember there's 4 students and there's 6 choices. Okay, so let me define or give a theorem to what we just did. Okay, so permutations. Permutations. So the number of ways to, quote, arrange. So the number of ways number of ways to arrange. Actually, that's not how you spell arrange. Spell check. Okay, so arrange. K options from a total of n possibilities. So from a total of n possibilities denoted by, and you'll see this symbol on your calculator, n, capital P, K, comma, read aloud, n permute, K is given by the following. So n permute K is actually n factorial divided by the quantity n minus K factorial, as we saw above. Okay, so let's note, actually let me move this up a bit. So note so there is no replacement with permutations. So there is no replacement. There's no replacement with permutations. Oh my goodness, spelling not my strong suit. So with permutations. And each distinct arrangement is a different permutation. So, and each distinct arrangement is a different permutation. So what do I mean by that? Well, for example, ABC will not be the same as ACB, even though I have the same three letters, but the arrangement is different. So this permutation is not the same as BAC. So the arrangement matters when it comes to permutation, and we don't replace the letters once we've chosen them. So that's what that note indicates. So, for example, so how many three-digit passwords? So how many three-digit passwords can be created from the lowercase letters. So from the lowercase letters, lowercase letters. Let's do little a through little z. So number one, let's do without repeated letters. Without repeated letters. So the word repeated here is equivalent to saying I'm not replacing any letters once I choose one. So i.e. Without replacement, no replacement. And we also want to note the letters, lowercase letters, A through Z. Do you agree that, note, there are 26 letters, right? So there are I can choose 26 letters, right? So the number from which I can choose is n equals to 26 letters. Okay, and how many do I want how many three-digit passwords? So I'm choosing, so K will be 3. So I'm trying to find 26 permute 3. So according to the formula, I claim that that will be 26 factorial divided by, actually let me do that in purple, 26 minus 3 factorial. And let me actually move that down one line. Okay, so what can I do here? How can I simplify this? Okay, so 26 factorial. Well, that's 26 times 25 times 24 times, well, I claim that I can write the rest of that as 23 factorial, right? And I'm going to divide all of that by, what's 26 minus 3? Well, that's 23. Ugh, what happened there? What is going on? What? Oh my goodness. Apple, the bane of my existence. Okay. Okay, so where was I? 26 minus 3 is 23 factorial. So the reason I'm writing it like this is I can now reduce the 23 factorials, and what's left will be 26 times 25 times 24. Okay, well, 26 times 25. I know 25 times 25 is 625, so add another 25, and that's 650 times 24. Okay, so let me do some lattice algorithm. So let me show you what the lattice algorithm is for multiplication. Let's do 6, 5, let's see, do I have room there? 0, times 24, so 2 and 4. So what I do for the lattice algorithm is I create a box. Notice I have one of the numbers on the top, one on the side. Doesn't matter which is which. But I'm going to break this up. Then I'm going to ask myself, okay, actually let me use shall I use yellow? Okay, so in this box here, top left, I have 6 and 2 that intersect in that box. 6 times 2 is 12. So now middle top, 5 times 2 is 10, which I put along the diagonal. 0 times anything is 0. Now let's go to the bottom row. 6 times 4 is 24. Middle bottom, 5 times 4 is 20. And then anything times 0 is 0. Now what I want to do is I want to create diagonals. Like so. Now mind you, I know you've got a calculator, but it's good to know these little tricks. So I'm going to take the sum starting on the right. The rightmost diagonal sums to 0. The next diagonal sums to 0. 4 plus 2 is 6. 2 plus 2 plus 1 is 5. And then 1. So I claim when all is said and done that this value up here, this product is 15,600 rather. Okay, so that's a lot. 15,600. Okay, plenty of passwords. Okay, let's do another example. Actually, let me move this maybe over here or something so we see where we got that. Okay. So now let's do another example, or actually this same example, this is without repeated letters, plural. Now let's do with repeated letters. So number 2, with repeated letters allowed. So repeated letters allowed. So this is no longer a permutation, because a permutation has no replacement. So this is just something we need to figure out on our own. So if there are repeated letters allowed, so what are the number of passwords? Okay, so how many choices do I have for the first letter? Let me say first letter. There's 3 letters, right? It's a 3-letter password. But the choices I have for the first letter, since it's a whole alphabet, I have 26 choices. Agreed? Okay, similarly for the second letter, put it here, the second of the 3. So second letter. It's with replacement. I can repeat, there's still 26 options. Now the third letter, I still have 26 options. Okay, so what I get then is 26 cubed. It's a large number. I don't care what the actual number is. 26 cubed is sufficient. Okay, hopefully that makes sense. Notice that's not a permutation. Permutation takes away each letter that's been used, right? Okay, so let's do another example. How much room do I have? So for example, this is a brand new example. Okay, so how many ways can we choose the letters A, B, and C? So how many ways? How many ways Can we choose the letters? The letters. A, B, and C. From a bag of alphabetic magnets. So from a bag of alphabetic. Let's do fridge magnets. Without replacement. So without replacement. If the order doesn't matter. Order doesn't matter. Doesn't matter. Okay, so let's consider. Let's say I have the arrangement A, B, C. Well, let's say I have the arrangement A, C, B. Or I could have the arrangement B first. Oh, do I have enough room? One line. Is there any way I can get one more line? Oh, I guess not. Okay. Well then, let me not put a space between them. Okay, I could have B first. And then, what color did I use for A? A. Or I could have C first. A. The B's. So these are the 6 possible arrangements, and I know arrangements won't matter. So in the first case, what do I have? So up here at the top, it looks like there's 26 ways to choose A first, but once I've chosen A, there's only 25 letters left. So there's 25 ways that I could choose B, and then there'll be 24 ways to choose C. Similarly, 26 times 25 times 24, or 26 times 25 times 24, or 26 times 25 times 24. So it's always the same way. So we have 26 times 25 times 24 different permutations of A, B, and C. So these are the 6 different permutations, right? 6 possible permutations. But what if order doesn't matter, i.e., all of these are equivalent? So hence, if order doesn't matter, we just divide by 6. So hence, if order doesn't matter, doesn't matter, we divide by 6, the number of different permutations, right? We divide divide, divide, divide by 6. Okay, so if we had n, what should I do? What color? So let's say the number of possibilities n was 26 letters, right? K was 3 because we want A, B, and C. So let's do 26 permute 3, but then I'm going to divide that by 6. So what does that give me? Well, 26 permute 3 I know is 26 factorial divided by, well, I've got this 6 down there, that's just coming along for the ride. And then I'm going to have 26 minus 3 factorial for the permutation. So what does this give us? This gives us 26 times 25 times 24 times 23 factorial for the rest of that factorial, all divided by, well, I can actually write 6 factorial as, 6 as 3 factorial, that is 1 times 2 times 3. And then 26 minus 3 will be 23 factorial. So I can then reduce the 23 factorial. I didn't know why I bothered to do that, but anyways. So what do we have? We've got 26. Well, 26, I claim, I know what I'll do. I'm going to write this as 2 times 13, and there's a reason why. 25, I'm just going to keep as it is. And then 24, I'm going to write that as 3 times 8. All over. Well, 3 factorial is 1 times 2 times 3. 1 times 2 times 3. So what I can do is I can reduce the 2, and I can reduce the 3. And so what am I left with? I am left with 13 times 25 times 8. Okay, so if I had 8 quarters, do you agree I would have $2? So I claim that this is 13 times $2 is how many pennies? 200. Okay, well, what do I know about 13 times 2? That's 26, right? So let's do 26 with 2 zeros. Okay, so hopefully that makes sense. And now, what did we just do? It's a permutation divided by a factorial. What is that called? That's called a combination. So combinations. And this is when order doesn't matter. So like the above, all of these were all the same. It did not matter. So the number of ways to, quote, choose. So the number of ways to choose K options from n, denoted by N capital C K, read aloud. So read aloud. N choose K. Is the combination defined by, is the combination defined by so N choose K. Well, it was the permutation N factorial over N minus K factorial, but then we tacked on there a K factorial we divided by. So it's like a permutation divided by N factorial, that is, i.e. N permute K divided by K factorial, same thing. Okay, so for example, and this will be the last example in this section. So for example, so how many ways can you choose? So how many ways? How many ways can you choose 5 cats from a shelter? A shelter housing 30 cats. Okay, so in this case, N, the number from which I can choose, is 30. How many do I want to choose? I want to choose 5. So K is 5. So therefore, 30, choose this time, choose in 5 is going to be, well, it's a permutation like before, so 30 factorial divided by, we're going to have 30 minus 5 factorial, but then we're going to tack on a 5 factorial over here. So it's just the permutation divided by K factorial, which in this case is 5. So this becomes, let's see, 30 factorial rather, will be 30 times 29 times 28 times 27 times 26, finally, times 25 factorial, all divided by 5 factorial, and 30 minus 5 is 25 factorial. So I can reduce the 25 factorial, and let's see what I can do with the rest of this. Okay, well, let me break up the denominator first, which is just going to be 5 factorial. So I know that 5 factorial is going to be 1 times 2 times 3 times 4 times 5. So what can I do with 30? Does 30 have a 2 and a 5 in it? Well, yeah, 30 is, let me color code, 30 can be written as 5 times 6, and 6 can be written as 3 times 2. Okay, then 29 just comes along for the ride. There's nothing I can do there. He's prime. So I've gotten rid of, what have I gotten rid of so far? A 3, a 5, and a 2. I just need a 4. Is 28 divisible by 4? Let me use a color I haven't used yet. How about orange? Does 4 go into 28? Maybe 7 times? And then I have 27 and 26. So let's see what I can reduce here. Okay, so it looks like I have 5 reduces with 5. I have 3 reduces with 3. And I have 2 reduces with 2. And then finally I have 4 reduces with 4. Okay, so what remains here will be a 29, a 7, a 27, and a 26. And I'm sure you guys can do the math on your calculator, but what should I do? Should I do the math? I don't know. I guess I could. So let's think about this, shall we? If this were 30 times 7, 3 times 7 is 21, so that would be 210. But I'm 1 shy, so that's 203. And 27 times 26, well, why don't I go ahead and do that off to the side using my lattice algorithm. So I'll have 27 times 26. Oops. Oh no, counting not my strong suit. I messed up. Okay, let's put this closer. There we go. Okay. Okay, so 2 times 2 is 4. 2 times 7 is 14. 2 times 6 is 12. And 7 times 6 is 42. Okay. So taking the diagonals here. We get, when we sum the diagonals, going backwards, 2. Oh, that's 10, so I carry the 1 and make that a 0. 4, 5, 6, 7, and 0. So I claim that that's times 702. Okay, so now I can do another lattice algorithm because I know it builds a lot of character. So let's combine these two. That is, let's do 702 times 203. Okay, so box here. At least there's lots of zeros in this one. Okay, so 7 times 2 is 14. 0 times anything is 0. 2 times 2 is 4. This whole row is going to be 0, thank goodness, as is this whole column. Okay, so 3 times 7 is 21. 2 times 3 is 6. Okay, so let's see what we get. Okay, so we have 6 in the first column, 0 in the next one, 5 in the next column, 2 in the next, 4, and then 1. So I claim all of this is 142,506. Okay, hopefully you had as much fun as I did doing this.